This class we are going to talk about equation of motion. So, what is equation of motion and how it can be derived? The derivation in itself is not that important, because ultimately we are going to use the various forms of equation of motion. Of the various forms of equation of motion, the one which is relevant to the system, to the geometry that we are trying to find out, what's the velocity distribution. But for any system, if one wants to write the equation of motion, essentially what we are doing for a fluidic system is we are writing the equation of Newton's second law of motion for an open system, in which the fluid is allowed to enter and leave the system. So, there is some momentum which is being added to the system due to the motion of the fluid, and by motion there are two ways by which, due to the motion of the fluid, momentum can come into the system, which we have seen before. One is the convective momentum, which is due to the flow of the fluid. So, some amount of mass of fluid per unit time is crossing this let us say this is the surface area. Okay. The amount of mass which crosses the surface area has a velocity at that point. So, mass times the velocity would give you the amount of momentum which comes in due to the actual motion, some amount of mass of fluid crossing the interface, which is nothing but the convective flow of momentum into the control volume. There are certain cases in which, let us say, the fluid is the control surface and the fluid is moving in this direction, and there is a gradient in velocity between this point and this point. So, this momentum, if this is y momentum gets transported in the x direction, if this is the x direction, due to viscosity, which is going to manifest itself as shear stress on this surface. So, the y momentum getting transported in the x direction must also be taken into account as a source of momentum coming into the control volume. Since it is taking place in a direction perpendicular to that of the motion, and since the principal reason by which this kind of momentum transfer takes place is molecular in nature, it is also known as the molecular transport of momentum or conductive transport of momentum. So, we have two different momentum due to the flow of the fluid. One is the convective transport of momentum, which is due to velocity, and the second is conductive transport of momentum, which is due to velocity gradient. Okay. You remember Newton's law of viscosity, in which the viscous transport is denoted by the velocity gradient, is expressed by velocity gradient and not by velocity itself. So, convective due to velocity, conductive due to velocity gradient. This is also known as the molecular transport of momentum or viscous transport of momentum. So, convective momentum, viscous, molecular or conductive transport of momentum. So, these are different reasons by which, different ways by which there is a change in momentum, net rate of momentum coming into the control volume. This control volume can also be acted upon by different forces. So, all the forces which are acting on the fluid inside the control volume, that should also be taken into account in the difference equation. And as a result of all these, there may be an unbalanced force on the control volume, and whenever there is an unbalanced force on the control volume, its momentum may change. So, the rate of change of momentum of the control volume, that rate of momentum accumulation inside the control volume can be expressed as the algebraic sum of rate of momentum coming into the control volume minus rate of momentum going out of the control volume plus sum of all forces acting on the system. So, this is the most general form of equation of motion for a fluid, which is nothing but again Newton's second law for an open system. That is what I have written over here. And here you can see that if this is defined as the control volume of side del x, del y and del z, with our previous notation that the x, essentially this is the x face, the y face and the z face. So you understand that the equation that I have just described would be rate of momentum accumulation, that is the rate of momentum accumulation in the control volume must be equal to the rate of momentum in minus rate of momentum out plus sum of all forces acting on, and this is important, acting on the system. So we would see that let's see how the convective momentum comes into the system. If I only look at this part, the face del y del z, del y del z, and let us assume that the velocity here is Vx. So the amount of mass which comes in through this face must be equal to del y del z Vx meter square, meter per second, meter cube per second, multiply it with rho, and what you get is kg per second. So this term up to this part tells you what is the mass which is crossing the x face having area del y del z. So del y del z rho Vx is the mass which is crossing the x face evaluated at x. Now in order to obtain the momentum, the x momentum, because I am writing the x component of the equation of motion, and the other components can be evaluated in a similar fashion. So if I am writing the x component, I am only talking about the x component of momentum. This is the amount of mass which is coming in. So the amount of x momentum must be equal to rho Vx, another Vx. So up to this is the mass of the fluid which is coming in through the face at x. So multiplying it with another Vx gives me the momentum, rate of momentum coming into the control volume. And when we talk about the momentum that's going out, so this would be again a Vx, but it is evaluated at x plus delta x. Similarly, when we talk about the x del z phase, so del x del z phase, this is the y phase, the amount of mass which is coming in through the y phase must be equal to the area times rho times the velocity, the y component of velocity. So the amount of mass which is coming in is equal to this much, but this amount of mass has an x component of velocity. So in order to obtain the x component contribution of this much of mass, this must be multiplied with Vx. I will go through it once again. The underlined terms simply tells you the mass which is entering the control volume through the y face having area del x del z. So this is the mass which is coming into the control volume through the y face, and this mass of fluid has an x. If I would like to find out what is the x component contribution to momentum, I simply have to multiply it with Vx. So mass coming in multiplied by the component of velocity in the x direction at that point would give me the amount of momentum that comes in to the amount of x momentum, that is important, amount of x momentum coming into the control volume through the face at y. Here also if you see, this is the mass coming in through the x face, and I multiplied it with the component of velocity at that point. So this is the total amount of momentum coming in through the x face. This is the total amount of momentum coming in through the y face. And if it is at y, evaluated at y, then this has to be multiplied by Vx and at y plus delta y. So, this would give you the x momentum that goes out of the system, out of the control volume through the phase at y. Similarly, I can write the z component. The amount of mass which is coming in through the z phase is the area, density and velocity of z component. Now, this amount of mass has some x component of momentum associated with it. In order to obtain that, I simply multiply it with Vx. So, mass is evaluated by the component of in the direction, and this amount of mass contains some amount of x momentum, the value of which is obtained by multiplying it with the x component of velocity at that point. So, similarly, this is to be multiplied by Vx and it is evaluated at z plus delta z. So, this is in, out, all are x momentum in through x phase, out through x phase, x momentum in through y phase, out through y phase, x momentum in through z phase, out through z phase. So, these 6 terms tells us the x component contribution of momentum to the control volume. Next we go into this. I will leave this figure in you to see, and here we are trying to find out what is the contribution of molecular momentum or conductive momentum or viscous momentum. Now, if you see the let's start with the y phase. Okay. The area of the y phase is del y del z. The shear stress, the x component of momentum gets transported in the y direction. So, the x component of momentum getting transported in the y direction must act on an area which is equal to del x del z. So, y direction has this much of surface area associated with it. So, the x component contribution in the y direction, this is the in term, must be equal to del x del z multiplied by the shear stress acting on the y phase. The one that goes out would also be equal to same thing, but evaluated at y plus del y. Let us try to again work out this x component of momentum getting transported in the z direction. So, if x component of momentum gets transported in the z direction, in order to obtain the total amount of momentum coming in, the viscous momentum which is coming in through the z phase, I must multiply this tau zx with the area of the z phase, which is del x del y. So, x component getting transported in the z direction multiplied by the area of the z direction, this gives me the rate of viscous momentum in through the z phase, and this is the rate of momentum of x momentum, rate of entry, rate of x momentum getting out of the z phase. So, these are the in and out terms. So, what is tau xx? Tau xx is the x component of momentum getting transported in the x direction. This is slightly unusual, because you get the x component gets transported in the x direction. That's only happen when, let us say, these are the packets of fluid and this is the x phase, which is delta y times delta x, and so these packets are coming towards this point, and there is a variation in velocity between these 3 packets. So, since there is a variation in velocity in the x direction, variation in Vx in the x direction, that means del Vx by del x is not 0, then by Newton's law, or by our understanding of viscosity, there must be a stress between these 3 packets of fluids, which will also be transmitted on this face. So, this kind of stress where the principal direction of motion and the direction in which the momentum gets transported are identical, they are commonly called as the normal stress. So, tau xx is nothing but the normal stress exerted by the fluid on the x face due to a variation in velocity of the x component. So, tau xx is nothing but the normal stress exerted by the flowing fluid on the x face. So, this is going to be the in term and this is going to be the out term. So, these 6 terms in total would give you the amount of momentum which is coming in to the control volume as a result of viscous transport of momentum. So, we have correctly identified in our equation of motion the rate of momentum in and the rate of momentum out, both for convective motion and the conductive motion. So, what is left right now is to identify what is going to be the pressure forces and what is going to be the body forces. So, let us assume that the pressure at x is P at x and pressure at x plus del x is P x plus del x. So, this pressure is acting on the x face, the difference in pressure is acting on the x face, the other pressure differences, they do not contribute to the x component of momentum, x component of force. Only the pressure acting on the x face and on the x plus del x face, they have contribution in the x direction. So, I need not have to consider P at y or P at z and P at y plus del y and z plus del z. So, this is acting on an area which is equal to del y del z. So, the pressure force, the net pressure force acting on the control volume is given by whatever be the pressure at x minus the pressure at x plus del x and multiplied by del y del z. Please remember, I am pointing out once again that we are writing this equation for the x component of momentum, x component of the forces, be it pressure or be it other body forces. Since they are all the other components, y and z components can be written in a similar fashion, and you do not have to write each one of those components separately. So, we have identified the momentum, we have identified the pressure forces, the only thing that is remaining is the body force which is acting on it. So, what is the body force? Body force must be equal to m, the total mass of the system, multiplied by the component of gravity. If gravity is the only body force, component of gravity in the x direction, since we are writing this equation for the x component of equation of motion. So, what is the mass of the control volume? It would simply be equal to del y, del x, del y, del z, that is the volume, multiplied by rho, which makes it kg, multiplied by g, which is gx, where gx is the x component of the body force. So, the body force term can simply be expressed as del x del y del z times rho gx. So, the body force here is simply going to be rho gx del x del y del z. This would be the body force term, and the rate of accumulation of momentum inside the control volume would simply be del x del y del z and del t of rho Vx. So, rho Vx would simply be, rho would be equal to kg per meter cube, Vx is meter per second. So, this would simply be equals kg per meter square per second, and what you would get here is then the momentum change. So, if you, this is meter cube and what you get is then kg meter per second and del t of that. So, this is the accumulation of rate of accumulation of, this is important, x momentum in the control volume is going to be del x del y del z del t of rho Vx. So, if I take the convective momentum, conductive momentum, the x component of the pressure force, the x component of the body force, and the rate of accumulation of the x momentum, then according to the equation, the first equation which we have written, rate of momentum accumulation must be equal to rate of momentum in minus rate of momentum out plus sum of all forces acting on the system. So, this equation, so all these terms together can be written, and I am not going to write the full form of the expression. What I am going to do is I am going to simply give you the compact form of this equation, which is rho. This is after some simplification. This equation in vector tensor notation is essentially known as the equation of motion, where the rho times dv dt is essentially mass per unit volume times acceleration. So, this is rho and dv dt, where here this is pressure force per unit volume, because pressure is Newton or force per unit area, then you have another del x in front of it due to tau. So, this is pressure force per unit volume, this is shear force per unit volume, and this is gravitational force per unit volume. So, how did we get to this equation from all the previous equations? Remember what we have done for the case for the x component of equation of motion. I have identified all the terms in there. Now, all these terms can be put into the equation which says rate of momentum accumulation is equal to rate of momentum in minus rate of momentum out plus sum of all forces acting on the system. So, both sides can then be divided by del x del y del z, and in the limit when del x del y del z tends to 0, then one can get a differential equation which is the x component of equation of motion, and in a similar fashion one can write the y component of equation of motion and the z component of equation of motion. All these three equations can be added to obtain the compact equation of motion once you express them in the vector tensor notation. So, no new concepts are involved beyond what I have taught you in this part. So, you can see the text and you can yourself see the simplifications that are made, which are only algebraic in nature without the involvement of any additional concept. So, I did not derive the entire equation in this. I have given you enough pointers for the fundamental development of the equation, and then I have told you how to combine these three equations in vector tensor notation, and what you get is the equation of motion in equation of motion when considering all the three directions. I would like to draw your attention to this equation once again, because each term of this equation are essentially this is mass per unit volume, which is rho, times acceleration. So, this is force per unit volume. This term is then force per unit volume. Here you would see that it is del of P. P has units of Newton per meter square, which is force per unit area, and because of this you have another length dimension added to the denominator. So, this is also going to come as force per unit volume. Similarly, shear stress is Newton per meter square. You have a del operator on it. So, this unit of this is also going to be Newton per meter cube. And similarly, in this also rho times g is nothing but the gravitational force per unit volume. So, this tells you what is commonly known as the equation of motion, and everything possible has been taken into account in here. So, if in this equation you introduce the restriction of constant rho and constant mu, if this is added to it, what you get is, so equation of motion when you add constant rho and constant mu, the equation simply, and plus equation of continuity. If you add the equation of continuity, since now you have constant rho, this is the previous equation simply boils down to this is known as the famous Navier Stoke's equation. Again, if you look at these two equations, the only change is it's a constant rho and constant mu. So, your tau can now be replaced in term, and tau can be replaced in this form, and you also have equation of continuity. So, the equation of motion for the special case when the rho and mu of the fluid are constant, then what we get is Navier Stokes equation, and this is the one which we are going to use in all our subsequent studies of fluid motion. There is one more simplification that can be thought of is if viscous effects are absent. So, if viscous effects are not present, that means we are dealing with an inviscid fluid. In that case, rho dv dt would simply be equals minus del of p plus rho g. This special form of Navier Stokes equation is known as the well known Euler equation. So, what we have then done in this class and the previous class is introduce the concept of different derivatives, introduce the concept of equation of continuity. We have seen what is equation of motion. The equation of motion for the special case where the density and viscosity of the fluid are constant would revert to an equation, would simplify to an equation which is more commonly known as the Navier Stokes equation. But all these equations, the equation of motion or the Navier Stokes equation, are nothing but the statement of the Newton's second law for an open system. And another fundamental relation in fluid mechanics is a special case of Navier Stokes equation where there is no effect of viscosity is absent. So, for a fluid of very low viscosity, or in other words truly for an inviscid fluid with no viscosity, idealized condition, what you get from Navier Stokes equation is known as the Euler's equation. And Euler's equation has so many uses, fundamental uses in fluid mechanics. It's the starting point from where you can start to obtain the Bernoulli's equation. So, Euler's equation is for inviscid fluid. Navier Stokes equation is the more common viscous fluids, in which case rho and mu are assumed to be constant. If they are not, then one has to go back to the fundamental equation which is valid both for steady and unsteady, constant rho or variable rho. So, constant mu, variable mu, Newtonian or non-Newtonian. So, equation of motion in itself is a complete expression that gives you the entire physics behind the motion of fluids and the momentum transfer. Now, all these equations, the Navier Stokes equation as well as equation of motion, are available in different coordinate systems. What would be the component equation for x component in Cartesian, cylindrical and spherical components, or similarly for other components in all three coordinate systems, are available in your textbook. So, what we would do is, in the next class we would see these components, and we will try to figure out how to use those for all the problems that we have dealt with so far using a shell momentum balance. And I am sure you will, all of you will see with me that the use of this right component of Navier Stokes equation for the problems that we have dealt before would essentially simplify our life a lot. So, we would be able to much more conveniently handle problems of momentum transfer if we start with the right component of the Navier Stokes equation, and from our understanding we would cancel the terms which are not relevant, and what would be left with is a compact governing equation that we should be able to solve using appropriate boundary conditions. That is what we are going to do in the next class.